You are listening to NASA in Silicon Valley, episode 67. Kimberly, tell us about our guest today.
Hey, Matt. Well, we have Roger Hunter. He's the program manager for the NASA Spacecraft Technology Program, where he actually oversees the progress of technologies that are demonstrated on small satellites. We also call them CubeSats because they're the size of a shoebox for a variety of missions for NASA.
All right, and this is a fun thing, the small sats, because you think of these tiny little, Kleenex box size small satellites. And it's not just NASA working on this stuff. This is like you have tech companies in the area in Silicon Valley working on this. You have a ton of universities and groups all working on this as a new platform.
Oh, yeah. And they're so popular that it's more actually encouraged to have outside non-NASA people be a part of this as our partners. They can actually pack so much in these little 4-inch by 4-inch cubes to go and ride on larger missions. Like this one coming up on November 11th. We actually have 4 small sat missions that are going to be taking a ride to the International Space Station.
Yeah, I get a kick out of this because you think of the big rocket with a big multi-million-dollar payload, really expensive to catch a ride on a rocket. But fortunately, there's little nooks and crannies on that rocket where you can put little small sats and people can take advantage of it.
Oh yeah, and it's a lot lower cost for the actual missions themselves. It costs about a quarter of the price of a larger mission. So, and even before that, which he may be talking about in his podcast, he was the project manager for the Kepler mission,
Nice.
which was our mission to see and look for Earth-sized habitable zone planets in the Milky Way galaxy.
So before we completely spoil the entire episode, just a reminder that we have a phone number. If you have any comments, questions, we are at 650-604-1400. You can give us a call just like our friend Raymond did, but Raymond called and said he had a question and asked us to call him back. And Raymond, if you're listening out there, go ahead and just call us back. Leave your question. We'll record it, and then we'll add that into a future episode as we go along. But for the folks who don't want to call and actually use your voice and you want to type it on the internet, we are using the hashtag NASA Silicon Valley. But before we jump in, I also want to give a shout out. We are a NASA podcast. We are not the only NASA podcast. And there's a new podcast that's going to be starting out of headquarters, hosted by NASA's very own Director of Planetary Science, Dr. Jim Green. This is called Gravity Assist. And basically, it's a virtual tour of the solar system and beyond, talking to a whole wide range of scientists. I think they're actually kicking it off with the sun and working their way through 10 episodes all the way until they end up talking about Pluto and beyond. But today, for this episode...
Now let's hear from Roger Hunter.
What brought you to NASA? How did you end up in Silicon Valley? Tell us about you.
I was working for the Boeing Corporation, running global positioning systems for them. And that was after I had a career in the Air Force, and I retired from the Air Force after 22 years.
Oh, wow.
And went to work for the Boeing Corporation afterwards because they had a position lined up that just seemed right up my alley, and it was all space systems again because most of the time that I was with the Air Force, I was doing a lot of space systems activities, whether it's designing ground systems or actually operating spacecraft or planning systems for the future.
Yeah.
And when I decided to retire from the Air Force, Boeing Corporation recruited me to come run their global positioning system activities in Colorado Springs. And it was in support of, guess who, the U.S. Air Force again.
Of course.
And so I spent a lot of time redoing some of the things I had done when I was in the Air Force and ended up managing a nice team of people there that was providing sustainment for all of the Air Force ground systems that controlled GPS satellites and also helping perform the analysis for the Air Force on how well GPS satellites were performing.
Well, even I imagine it's very much the same way because you're thinking of NASA and you think of the astronauts and how much infrastructure and humans go to support them doing their work. I'd imagine it was probably the same for you in the Air Force. There's you have the people who fly the planes, obviously a much larger group than astronauts, but there's a whole
there's a whole infrastructure that supports the team.
Yeah.
And matter of fact, they talk about the pointy end of the stick when you're in the Air Force.
Okay.
We were the ones that actually are, if you will, guns on target or bombs on target, things like that. But there's a whole infrastructure behind that helps that team be successful. And it was while I was working for Boeing in Colorado Springs that I received a phone call out of the blue from the former NASA Ames Center Director, Pete Worden, and one of his directors, Alan Weston. And I thought it was just a casual conversation at first, and all of a sudden he says...
then the pitch came.
The pitch came. Says, we would like for you to come work with us on a mission called Kepler. And I didn't know that NASA had a mission called Kepler, because I was keeping it with NASA at the time, and I knew who Johannes Kepler was from my my math and physics days at the University of Georgia.
Yeah.
And they said, "Oh, we're building a telescope to go search the galaxy to see if there are other Earths out there." And I said, "You have my attention." I said,
"Go on,
go on. Tell me more about when you're going to do this." And this was early 2008, and the Kepler Space Telescope was still under development, and they wanted somebody to come work with a team who had some experience managing large teams and also had experience bringing a space telescope or a space system from development into operations. And I said, well, where do I sign? And he said, you only get 2 chances in life to go either one, work for NASA, or run a mission called Kepler that is in search of one of the most fundamental questions that humankind has always had. Are we alone?
Yeah, absolutely.
And you want to go look for, you think about this when you're a kid.
Yeah,
you look in the sky and say, is there another Earth out there? And I thought, wow, we're actually going to go do this. NASA is actually going to go build a telescope called Kepler to go look for another Earth. And I said, where do I sign?
Exactly. Well, it's like instead of daydreaming or about science fiction, you get to do science fact.
Exactly.
And actually prove, is this a real thing or not?
You're right, because it was turning science fiction into science fact. And so I left Boeing and moved to Silicon Valley in early 2008. And we helped continue the development of the Space Telescope until we launched it in early 2009. And so I was a Kepler program manager for about 6 years. And towards the end of the baseline mission,
the primary mission,
Pete Worden, who's still the center director, asked me to move over into a new area called the Small Spacecraft Technology Program. And that's what I've been doing for the last 2 or 3 years at NASA.
So moving over into small spacecrafts, was it mainly like just looking at like smaller missions, or were you even kind of like moving into the territory of like CubeSats and that kind of work?
It's both. It was moving into CubeSats, which is sort of a new paradigm out there, because we've been, we as in NASA, but also academia and industry, have been looking at these small spacecraft, which are basically the size of a tissue box or the size of a loaf of bread. And looking where technology and electronics revolution has brought us, we were thinking, we can actually do science with these things.
Yeah.
And so that's what's happened. That's where the industry has brought us now, and NASA is now looking at using spacecraft of this size to actually go do science.
And so I'd imagine for, especially even coming from like when you moved into the Air Force and you're working, I'm sure there was obviously some set missions, set programs, some projects that, you move in and you're kind of filling in a position on the team and it's already a well-oiled machine. But especially even at NASA, there's certain, whether it's a telescope that's already in the sky, a mission that's already ongoing, but you're going in to do small spacecraft. You're stepping into something that like hasn't been done. You're almost kind of building it from scratch. That's got to be a whole different thing. It's not like you're moving into something that's already established.
It's a new mindset, because when you look at many of the telescopes that NASA has flown before, they're rather large. They are big entities.
Millions of dollars.
Millions and billions of dollars in some cases.
Wow.
And they're called great observatories because of the magnitude of the mission that they're either conducting or the amount of money and time that has gone into the development of these things. They're essentially one-offs. No one had built a Hubble before Hubble was built. No one had built a James Webb Space Telescope before it was built.
Yeah.
And they were one of a kind, and they are artisanal, if you will. But we are
custom-made.
They're custom-made. They're custom-made units. But we're looking at CubeSats and small satellites as more of a commodity. How can you make lots of these and go do a mission with them? And if a few of them fail, you don't jeopardize the mission.
Yeah.
Think about that from the perspective, if a singular system on board one of those giant spacecraft fails, you're in jeopardy of losing the mission itself. You build in redundancy, of course, but now we're looking in making these small spacecraft much more redundant, much more robust, much more flexible.
And even for like a large thing, like a Hubble or a Kepler, there's a whole lot of you have to be very conservative on what you're doing. You have to make for sure you have the redundancy built in. This thing is going to work. We're not wasting millions of taxpayer dollars on this thing. So you have to kind of just be very conservative and thoughtful.
Right.
But for something like small sats where you're kind of opening it up, you're in an opportunity where you can get kind of ambitious.
Right, you can
stretch your legs out.
You can take more risk.
Yes, exactly.
That's the name of the game in the small spacecraft area, because you can build more of them at a much lower cost. And when you can do that, you can take more risk with the things that you're trying to do.
And so talk a little bit about starting those programs and working in those early days. How do you even begin something from scratch like that?
Well, you do it from an envelope.
Nice.
Sometimes you scratch these things on the back of an envelope.
Yeah.
But we're looking at what are the things that we can do with the electronics and technology revolution that has brought us to today, and just package that into something that you can go do science with. For example, if you look at your smartphone.
Absolutely.
We have built a spacecraft that we call PhoneSat.
Okay.
Because we want to prove that you can take the guts out of a smartphone and put it into one of these 1U size, which is like 10 centimeters on the edge, a CubeSat, 10 by 10 by 10 centimeters, and put the guts of the smartphone inside that, launch it into space, and see what it does.
Oh, nice.
And we turned that into the first spacecraft was called PhoneSat because it was based upon a smartphone.
Yeah, I mean, and it makes sense because you couldn't have done this in the 80s or in the 90s.
No, you couldn't.
This is only with the advent of small, smartphones and electronics getting smaller and smaller and smaller, and batteries and sensors and cameras. Now it's able to take advantage of it.
Absolutely, because you look at the processing power in your smartphone today, and the computers back in the 60s, it took a room size to provide the processing power that little smartphone gives you today.
And so talk a little bit more about PhoneSat. So is this just one phone in one, are these CubeSat things, or is it a swarm of them, or how does it work? What are you doing?
Well, the first ones are just singular, and we just want to prove that the technology works and we can get it into space.
You got it there.
Got it there, and then and see how it reacts. And of course, the first couple we broke them.
Nice.
But that's what happens. You break these things, but you learn from that. And then the next ones, you get a little better, and then you get to the point where you don't break them. And now we're looking at, for example, let's think about how GPS operates. That was a constellation of spacecraft. To provide you worldwide coverage, you needed an entire constellation. Well, the way NASA does science.
When you say constellation, what for people?
That's many spacecraft orbiting the Earth, and they're all interconnected. They're all doing the same kind of mission.
Okay.
Now, think of having a bunch of satellites that are oriented towards science, and you want to collect a lot of science data because the more data you have, the better the science. And so if you can orbit a bunch of satellites at one time, and they're all very small, you can launch them all at once on one rocket, deploy them, and then collect science across an entire globe or across an entire region, allowing you more data collection, which gives the scientists more data to analyze.
And I'd imagine that also plays into, typically a satellite is looking at one part of the Earth, and it can't look at it all at once.
That's
obviously.
right.
But with many of these smaller satellites, you can cover a bigger width.
Exactly. Yes. As opposed to just collecting data singularly across a path across the Earth.
Yes, exactly.
As the spacecraft orbits the Earth, you can deploy many of these and collect data from many different vantage points. And when you can do that, then that improves the science that you can collect, and it informs the scientists better about what Earth science is or what the Earth is doing. And for example, climate change. If you can collect multiple data points of science across the entire globe simultaneously, that can give you a better feel of how the climate is reacting, how the climate is changing, and how you can assess what's going to happen on the surface of the planet better.
And so I'm guessing during the early days of starting, working with small sats, CubeSats, doing this kind of stuff, was it primarily NASA researchers and NASA engineers and scientists working on this stuff? At what point do you start branching out into, universities, companies, startups? How does that
Oh, in many cases, the universities and the other industry were leading the way.
Oh, wow.
Matter of fact, when you look at the form, fit, function of CubeSats, they were established at the university level. And NASA is following this. Matter of fact, a lot of the innovation that's going on now is happening at university or in industry. And NASA is partnering with a number of these universities and a number of these industries across not just the United States, but around the globe to better to accelerate the development in small spacecraft technologies.
And I know a big thing that Ames has been working on are what we affectionately call the virtual institutes,
right?
Where it's not only just NASA, working with like special Space Act agreements with other people, but it's actually creating an institute, bringing in all of these different communities who are working on this stuff, so that people aren't like siloed and they can share information, and share their progress. And that even moved into the whole virtual institute for small satellites.
Correct. We've had some virtual institutes already established that are oriented towards, for example, solar system exploration and research. And so NASA saw the need to copy that success from small spacecraft perspective. And so now NASA has established a small spacecraft virtual institute, which is going to hopefully mimic the success that we've had in these other virtual institutes and further the sharing of knowledge, further the collaboration, further the coordination between not just NASA centers, but across academia and industry alike, so that we can all take advantage of the revolution that's going on in electronics and technology to make small spacecraft even more capable and flexible than they are today.
Well, even thinking about just like, the people who are listening to this podcast, or your students, interns who are wanting to get jobs with NASA, getting jobs working in the space program or in the space industry, it's like, now those people who are applying for these internships, applying for jobs, could literally have small satellite missions on their resume that they did through high school or college. They've already done this stuff.
That's true. As a matter of fact, there's a number of universities that are flying their own missions.
Oh, wow.
And they are using that to further the research and development that's going on at their institute so that they can infuse that into industry. There's even elementary schools that are now building small spacecraft and launching them.
So talk about a little bit about yourself, like your day-to-day, what you're working with on small sats now. What do you come in? You get your coffee, you open your laptop.
Yep.
How's it look?
Well, we're actually marching towards some upcoming launches. And so we spend a bit of time right now on what we call the end game of getting the spacecraft into orbit. We have 2 spacecraft that are launching on September the 12th.
Okay.
And they're going to go up on a Cygnus resupply mission to the International Space Station. And these 2 spacecraft, one is called OCSD, and it's an acronym for the Optical Communications and Sensor Demonstration.
Of course, NASA, you have to have an acronym.
Oh, absolutely. We live by acronyms.
Exactly.
And another one is called ISARA, which stands for Integrated Solar Array Reflector Array. Now, both of these are demonstrations of first-time uses for NASA and for anybody for that matter. And this is another example of where NASA is at the cutting edge of developing some technologies that are going to improve our small spacecraft technology. Now, the first one, OCSD, is going to demonstrate for the first time laser communications from a CubeSat to Earth, and also laser communications from the Earth to the CubeSat. We think that is necessary given the expected number of small satellites that are going to be launched in the coming years, and there will be many spacecraft out there. And the regular electromagnetic band, radio frequencies are getting crowded, and so we see the necessity of moving to communication by laser or communication by light.
I was going to say, normally when you're talking about communications, you specifically said laser communications.
Yes.
So the sci-fi, sense is going off of like, lasers and communications. So this is basically electromagnetic. I imagine, it just doesn't work the same, I guess.
Yeah, no, it doesn't. There's a difference.
There's different factors involved.
There's a lot of things you have to take into consideration when you're using laser communication from space. You have to point the thing accurately because when you're pointing a laser, it's very precise in where you originate the laser from and also where you terminate the laser on the ground.
Yeah.
And so we have to make sure that type of pointing is accurate enough so that you can complete, if you will, the circuit between the small spacecraft and the ground terminal. Now, we'd only done laser communication once before from it was a bigger spacecraft, and it was from the moon. Remember Laddie?
Yeah.
And that was just one-way communication, and that was it gathered a lot of information on the Laddie spacecraft, and then we blasted it back down to the Earth, and it worked perfectly. Well, now we want to extend that to CubeSats. Okay. So no one's done this before, and so when this spacecraft launches on September 12th, it's going to spend a little bit of time, inside this Cygnus resupply capsule while it's attached to an International Space Station, because they're going to resupply the space station. They're going to take material off the capsule and then exchange stuff that's used on ISS back on the capsule. But then the Cygnus capsule will maneuver away from the International Space Station to a higher orbit, and then it will deploy our CubeSats. We will go through a readiness check out of the CubeSats, and then we will conduct the experiment. We will laze from the ground to the CubeSats, and then when they collect more data, they will laze from the CubeSat to the ground, and there will be 2 of them that will be doing this mission.
And this is critical because, if you can prove this, make it show that it works, have it, functioning, then that is just for the next generations of small sats that go up. They're like, hey, we've already done this. Let's add this and then have other functionality put on top.
Exactly. And there will be other users out there, whether they are within NASA or within the Air Force, perhaps, or within industry who will be very interested in the success of this mission. They want to see that this laser communication is going to work, and if we can prove that it does, then they will welcome that new technology into their systems.
So talk about the other one.
Okay, integrated solar array reflect array.
I was going to see if I could remember. All I could remember is array something.
Yes.
So I'm glad you have it.
This is another first of its kind. In this case, we have the first demonstration of Ka-band communications from a CubeSat. But what's also interesting about this is that we have an antenna on board the CubeSat. One side of it is the antenna, but the other side of that structure are solar cells. So you have a part of the spacecraft that provides 2 functions. One side helps reflect the Ka-band or the radiation, or the signal from the CubeSat to the ground, while the other side of that structure is collecting solar energy and providing power to the spacecraft. So this will be a first demonstration of that technology as well.
Oh, wow. And where do you see that could go, for other people? I mean, is it just more of a way that these small sats can gather more power apart from just the...
It's like a dual-use technology.
Yeah.
For example, you're using it to not just generate power for your spacecraft, but you're also using it to help generate your communications for your spacecraft.
Oh, it's just just self-sustaining.
Yeah, you become a dual-use technology essentially. What happens in this case is that most of your subsystems are one function. And this is a step down the path of making multifunctional spacecraft.
Oh, wow. And then that just exponentially grows. Not only do you have multiple small satellites out there, you have your swarm, but then each one can do multiple things.
Yes. Think of the chassis for your car. It serves one function.
Yeah.
And for your spacecraft, you have a chassis that you bolt all of your things inside, whether it's your sensors, your batteries, or your attitude determination control subsystem. Think if that structure was also not only providing a form for your spacecraft to attach parts to, but also served as a battery. Now you're getting into a spacecraft that's multifunctional, and that helps you reduce the weight of your spacecraft, but also gives you more capability and more robustness to your spacecraft. Those are some of the things we're working on for the future.
And so if I understand, you have another launch coming up in October that's apart from these 2.
Yes, it's apart from the first 2 I mentioned. This one that launches in October is called CPOD, for CubeSat Proximity Operations Demonstration. And
always with the acronyms.
Always the acronyms.
Yeah.
And this one is going to be the first demonstration ever of 2 spacecraft, 2 small spacecraft, 2 CubeSat spacecraft that are going to dock with each other.
Okay, I remember we are recording this in June, and we just recently had the Centennial Challenge of Small Sats awards were announced, and we have animations. I've seen this of the small sats circling each other, docking.
Yes. Yeah, they deploy attached to each other.
Okay.
And then after they maneuver some distance from the stage of the rocket that gets them into orbit, they will detach, move to a distance, tens of kilometers, and then we will initiate them. We'll turn them on. And then they will start looking for each other. And then they will start homing in on each other, and they do this circular pattern.
They're kind of circling around.
Yeah, they circle around, and then eventually they will come together, and there is a mechanical docking mechanism, like little fingers, and then they grab each other, and then there are electromagnets that are turned on, and it finishes the docking of the two. We've never done this before for CubeSats, and so we want to demonstrate this for the first time. Why is this important? We envision that many of the large observatories that we may send into space in the future are going to be manufactured on orbit and assembled in orbit, and which means that some parts of these spacecraft will have to dock with each other. And so we're proving out some of the concepts today that will enable some of the missions that we will fly in the future.
Wow, and you just think about that. You have the laser communication, so you're gathering data and sending it back, probably in like real time. They're doing multiple functions, they're dual use, but then also moving it into, they can dock, they can separate, they can form, have the swarm of small sats that are able to serve different functions.
Exactly.
And so for anybody who's listening, who's like, you've piqued their interest, they're all about learning more about small sats. I believe you have nasa.gov/smallsat.
Right.
So for anybody who's looking for information, I'm sure there's a lot of information from the Centennial Challenge that happened in June, and all that you could hope for anything to learn all that there is about small satellites.
Yep, just Google NASA and Small Spacecraft Technology Program.
In the show notes, we'll add links to everything, so if anybody has any questions, want to learn more about that. Also, we are on Twitter at NASA Ames. We're using the hashtag NASA Silicon Valley, so if anybody has questions for Roger, feel free to ping us there, and we'll get back to Roger and go ahead and send some responses back and forth.
Sounds awesome.
So, excellent. Well, thank you so much for coming over.
No, thank you.